Hello, my name is Jared Skeens and welcome to the Zoom room. Today we want to look at Pure Math 3, Integration, Part 5, Differential Equations. Now, we mentioned differential equations in the previous video, that it's a part of the integration unit. And so I have my own little, again, mental map of helping me through the stages. These are big point questions, multiple steps. And so you need to have that mental map to help you progress through these pretty big questions. And so what I have is separate, integrate, find, C. That's the 3 steps that help me through differential equation problems. The separate is going to have to do with the differentials. We'll talk about that in a minute. Integrate actually goes back to what we covered in the other integration sections, and that is simplify, integrate, evaluate. In other words, simplify is what do you have to do to prepare it to be integrated. Then the integrate is your, executing the formula. And we don't really have to evaluate with differential equations because we don't have bounds of integration, but instead we have find C. Since there are no bounds of integration, we have the integration constant that we need to find. So having said that, let's just jump right in so that I can kind of walk you through this mental aspect, and also so that we can practice seeing these multi-step problems. So let me take us to the first question here. It's from Winter 18, paper 32, number 6. Says a certain curve is such that its gradient at a general point with coordinates x, y is proportional to y squared over x. The curve passes through the points with coordinates 1, 1 and e2. By setting up and solving a differential equation, find the equation of the curve expressing y in terms of x, and it's 8 points. So a couple of things that you need to notice. First off, and I was going to use this example a little later, but since it's really not that complicated, I put it at the beginning. Normally, Cambridge will give to you the differential equation. There are a few times where they do not, and this is one of those times. They do not give to you the equation. You have to generate it yourself. Usually, and most, if not all the time, it's going to have to do something with gradient, because your slope is change in y over change in x. So that's your dy dx, that's your differentials. And another very important word to notice is proportional. This also occurs especially in the differential equations that they don't provide for you. You might also see it in one where they do provide it for you. But this proportional means you need to provide the proportionality constant, and I use the letter K. Notice you do not see a K in this part over here. This y squared over x is the part they have given to you, but this proportional is the proportionality constant. So that's very important in getting started. If you don't start right, you're going to lose most of those 8 points. So you really need to pay attention. I would write it in your notes that proportional means proportionality constant, and you need to substitute a K into your equation. That is also why they give you 2 coordinates. Generally, they only give you 1 so that you can find the plus C at the end. But now we have to find the K and the C. So that's why we have 2 sets there. And also notice at the very end, expressing y in terms of x. It's important to know what variable they want as the subject, and also in terms of what kind of expression on the other side. So these are things that you need to look for at the very beginning. So let's get started and go back to the board. Okay, so separate, integrate, find, see, that's our mental general pathway. Says the slope or gradient, same thing, is proportional, that's our keyword, to y squared over x, and here are the coordinates that they provide for us. So slope or gradient this is our differentials, our dy dx. So somewhere in the reading of the problem, if you have to generate the differential equation, then you need to have some sort of way of determining what the differentials are. And since it's slope, it's just dy dx. Equals, or is, that's our equals, proportional to, here is our proportionality constant. Don't forget it, the k, very important to get you started off right. And then it's proportional to the y squared over x. So it's just k times y squared over x. So this is our differential equation. Like I said, most of the time, as you'll see in the next examples, Cambridge will provide for you the differential equation, but there are a few times where they do not. Okay, so now we need to go into the first step. Now that we've generated the differential equation, now we need to work our way through this process. So we need to separate the variables, meaning our y variable needs to go with its differential. If you remember in our previous integrations, we usually had the integral of x's with a dx or thetas with a d theta. We need to put the variables with their differential. So this y squared needs to go with the dy. Since the dy is on top, just keep it over here. We want the differentials to be, we don't want them in a denominator. We want them to be on top. So since it's already on top, we want to leave the dy here. So we just divide the y squared to the other side. That gives us 1 over y squared. And of course, the dx we want to multiply to the other side for 1 to get it out of the denominator, but also so that it's over here with the x. So we have k over x dx, and we have 1 over y squared dy. As far as the constant, if you have a numeric constant, or in this case, our proportionality constant, really doesn't matter which side it's on. So you're going to have to decide which one kind of fits better with what you're working with, but we're just going to leave it right there. Now we go into the integrate part, and the integrate, remember, takes us back to that other mental pathway. Simplify, integrate, evaluate. We don't have to do the evaluate, so it's just simplify and integrate. So we need to identify what formula or where we're at. Remember, I listed those 5 things: basic rule, the derivative over the function, substitution, could either be U substitution or trigonometric identity, integration by parts, or is it partial fractions? So when we look at this, is this a simple basic rule? And actually it is, but we want to make it in exponent form because the rule is in exponent form. So we want to change this actually into a y to the -2. So that's what we did over here. And integrate y to the -2 dy. This one is already okay. The top is the derivative of the bottom. This is your logarithmic one. And so we can identify the methods that we're going to use: basic rule and logarithmic rule. So that's the simplify part, is preparing it to be integrated. Then we do the integrate. So when you integrate, you add 1 for the basic rule and divide by that number. So we end up with a negative y to the -1, which is the same thing as 1 over y. So a negative y to the -1, or a -1 over y, equals, and then the constant just goes out in front, and 1 over x becomes ln x. I put absolute value to make sure it's positive. And then plus C is our constant of integration. Now you ask, why didn't I put a plus C on the left side? Well, you've got two constants, and if you subtract the one from the left over to the right, it does not make it cancel out. C represents an unknown number. Might be 0, might be 10. So you can't just subtract them and make them go away, but the C is very flexible and can absorb any other constant. So if you divide it by 2, it's still a constant. If you whatever you do to it, it remains a constant as long as you're not putting a variable into it. But instead of putting it on both sides, I just put it on the right side. So if we took our plus C from here and our plus C from here, and we subtract it, it does not make it go away. It's still a constant, okay? So it's a very flexible constant, but it is still a constant. We don't know that those two constants are actually the same, but we can put it together. I just put it together on the right side. Okay, so that's our plus C. That's the combined constant. Okay, so now we've integrated it. Now we need to find the value of C. We also need to find the value of K. So we'll take our first points that are given to us and plug it in and see what we get. So we have a -1 over 1 equals K times ln 1 plus C. And interestingly enough, ln 1 becomes 0, so it cancels out the K. Otherwise, you might have a system of equations you might have to work with. But in this case, the K canceled out, so C is a -1. Now that we have that, we can use our second set. -1/2, because we put the 2 in for the y, equals K ln E minus 1, because now we know C is a -1. And ln E cancels, the ln and the E are opposite, so it cancels out. Basically makes 1. 1 times K is K. If we add 1 to the other side, K is 1/2. So now we have our complete equation here. -1 over y equals 1/2 ln x minus 1. So this is correct, but not yet in the right form. At the very end of the question, it says express y in terms of x. We don't have y as the subject yet. It's almost there. What we have is a -1 over y. So we need to make sure that y is in the numerator by itself. So the first thing I'm going to do is multiply the negative through to get rid of that. So we have 1 over y equals 1 minus, changes the -1 to positive and our logarithm to negative, -1/2 ln x. Then you just flip both sides over, or if you want to multiply y over here and divide all that over there, and you get y equals 1 over 1 minus 1/2 ln x. There's not really anything particular wrong with this, except generally we don't like complex fractions. That is a fraction within a fraction. So we need to deal with this 1/2. There's more than one way to do it. What I've done is just multiplied top and bottom by 2 to cancel it out. And so we end up with a 2 on top and a 2 minus ln x on the bottom. This is the answer that you'll see in the mark scheme, but you'll also notice it says OE, which means or equivalent. So in other words, you could have taken that 1/2 and you could have moved it up as the exponent, and you could have ended up with 1 over 1 minus ln root x if you wanted something like that. So there's several different ways that the form could be in, as long as y is your subject. You don't have a complex fraction. You want to avoid complex fractions. And so your y is now in terms of x. Okay, so if you don't end up with exactly what the mark scheme has, check to see if it says OE, and if it does, then you want to make sure that what you have is still the same thing. As long as you can justify what you did, you want to make sure that those are the same, at least in value, if not in form. Okay, so this is what we're doing. separate, integrate, find C. In this case, they did not provide the differential, and the keyword proportional was our proportionality constant. And then we worked through from that point was pretty much the same as our other integration methods that we used. And then at the end, we had to make sure that our subject was correct. Okay, I'll set up the next example for us. Okay, let's look at our second example here. It says the variables x and theta satisfy the differential equation. And notice here they give you the differential equation. Sine 1/2 theta dx d theta equals x plus 2 times cosine half theta. For 0 to pi for theta, it is given that, so by the way, you're in radians. If you ever use your calculator, make sure you're in radian mode for this. It is given that x equals 1 when theta equals pi thirds. So that's our coordinate that they give. Solve the differential equation and obtain an expression of x in terms of cosine theta. So pay attention to not only the subject, but also what it needs to be in terms of. So x in terms of cosine theta. So let's go back here to the board. And we see here is the differential equation they gave us. Sine half theta dx d theta equals x plus 2 times cosine half theta. And here is the coordinate they gave us, x equals 1, theta equals pi thirds. So again, we start with separate. Separate your variables with the differential. We already have dx on top, so we want it to stay there. So we're going to divide the x plus 2 to the other side. So we get 1 over x plus 2 times dx. Then we need to multiply the d theta to the other side, and we need to divide the sine 1/2 theta to the other side. So we get 1 over x plus 2 dx equals cosine half theta divided by sine half theta times d theta. So that's the separate part. Now the integrate. First, let's look to make sure we know which rules we're working with. So on the left side, this should be obvious that this is a logarithm. The top is the derivative of the bottom. So this is a logarithmic function. Then it's not algebraic. So you should come to the conclusion it's logarithmic. This one might be a little tricky. You might, because when you look at your formula sheet, you're not going to see cotangent. If you switch this to its reciprocal function, the cosine over sine makes cotangent. But if you look for cotangent in your integrals, make sure you're looking at the integrals, there's not a cotangent there. It's not in your basic rules. So you need to back off from that idea and start looking through the list again. Number 2 is the top derivative of the bottom. The derivative of sine is cosine. Don't worry about the argument, the coefficient. That doesn't bother us. What we need is the trig function. The derivative of sine is cosine. So this is also actually a logarithmic rule. Okay. So work through that list before you just start trying to do something. Is it basic rule? Is it derivative over function, which is logarithmic? Is it substitution, which could be a trig identity? So that's the kind of the two that you're wrestling with there. Then the by parts, and then partial fractions. So get that in your head so that you can think quickly and clearly what you're wanting to do. So now that we've identified that, we'll integrate both sides. The integral of 1 over x plus 2 is ln of x plus 2, again with absolute value. And then the integral of this is ln of the function, which is sine 1/2 theta. And then don't forget you need a 2 in the front. So to make sure that you get it right, don't forget to work backwards. The derivative of ln of x plus 2 is 1 over x plus 2. The derivative of the argument is just 1, so that one's fine. The derivative of ln of this is 1 over sine half theta times the derivative of the inside. Notice you have the trig function, which is your cosine half theta, but you also have the argument of the trig function, which is you're going to divide by 1/2, which is the same thing as, or you're going to multiply by 1/2. So you need a 2 out here so that when you multiply by the 1/2, it cancels the 2, giving you no coefficient at all. Okay, so just think it through backwards to make sure it comes out the way you want it. And then you put the plus c and we keep it here on the right-hand side. Now we need to find c. So we plug in our coordinates, 1 for the x, so we get ln 3, pi thirds for the theta, so pi thirds times 1/2 is pi sixth. Pi sixth is the same thing as 30 degrees, and sine of 30 degrees is 1/2. So we get 2 ln 1/2 plus c. Now you could put the 2 up here as the exponent. For right now, I just left it down here during this stage, but now that we're here, I put it up here so we get ln 3, and that when you square it makes a 1/4. Subtract that to the other side to get the c by itself. So ln 3 minus ln 1/4 equals c, and subtract means you divide the arguments. 3 divided by 1/4 is ln 12. So ln 12 is the value of c. So I come back here and rewrite it out, ln of x plus 2. Now I've moved the 2 up as the exponent. You could have done it earlier. I waited till now. And it's a square. Remember, it squares the trig function. It does not square the argument. Don't square the argument of the trig function. It squares the trig function itself. So it's ln sine squared half theta plus our c, which is ln 12. Now we need to make x the subject, because it said express it x in terms of cosine theta. So first, let's get the x by itself. So we need to exponentiate both sides to base e. So on this side, the e and ln cancel, leaving us with x plus 2. Now on this side, I rewrote it again because the entire side is exponentiated. It does not distribute through add and subtract. This is now an exponent rule. And remember, when you add exponents, it's because you multiplied like bases. So you're kind of using the exponent rule backwards. And we talked about this in the logarithmic section as well, and if you watch those videos. So when you multiply like bases, you add exponents. So we're just going backwards from the exponent rule, putting it back into the like bases and changing the add to multiply. Now they can cancel out. And so we get x plus 2 equals. Here our logarithm and exponential cancel out, leaving us with, this one cancels out and becomes 12. So that becomes the coefficient because there's no variable there. So this one, 12, gets put in the front times the sine squared 1/2 theta. So we have that. And then we just subtract the 2 to the other side. Now x is the subject. But that's not the end of the problem because it said to put it in terms of cosine theta, not sine theta. So now we're going to have to work with identities. And this one's a little bit tricky. What we're looking for is where a sine squared transforms into a cosine. So let me just show you really quickly so that you don't get lost in the formula sheet. Here's our formula sheet right here. Scroll through to the identities part. And here's, I think I missed the identities. Here we are, right? Here's the identities. So when you look through the identities, normally when you see sine squared, you're looking at this one right here, sine squared, but that turns it into a cosine squared, not cosine. And so And if you put cosine squared in and try to get cosine by itself, you're going to end up square rooting your x, which doesn't make x the subject anymore. So this one actually won't work. So what you're looking for is where you have another sine squared. And if you look right here, you have a sine squared that becomes a cosine. This is the one that you're looking for, but we need to rearrange it a little bit. Okay, so take this one, cosine 2a equals 1 minus 2 sine squared a. Let's go back to the board. So cosine 2a equals 1 minus 2 sine squared a. Don't worry about the argument right now. We're trying to take sine squared and convert it to cosine. So let's solve for the sine squared. Okay, so let's add it to the other side and subtract the cosine 2a and then divide by 2. So cosine squared a equals 1/2 minus 1/2 cosine 2a. So I kept using the a, kept it in its identity form until I get the sine squared by itself. So now we have sine squared going to cosine. Now we can substitute the 1/2 theta in for the a. So our sine squared 1/2 theta. And over here, the 2 and the 1/2 are going to cancel, and it's just going to leave us with cosine. So when we substitute it in, we get x equals 12 times this 1/2 minus 1/2 cosine theta, because the 2 and the 1/2 canceled, just leaving the theta, and then the minus 2 at the end. So distribute the 12 through, and we distribute the 12 through. We get 6 minus 6 cosine theta, and then the minus 2 from the outside. 6 minus 2 is 4, minus 6 cosine theta. Now we have x as the subject and in terms of cosine theta. So you can see that these problems are big point values because they are multi-layered. And again, the key to success is 2 parts. One, your mental ability to work through the question in an organized manner. And second of all, your execution of the different things that you're doing, whether it's the integrating or whether it's just substituting in your trigonometric identity. So I hope that this helps you. And I've got one more example for us that I'll set up. Okay, let's look at our last example for this video. Here we have the variables x and t satisfy the differential equation 5 times dx dt equals 20 minus x times 40 minus x. It is given that x equals 10 when t equals 0. This is a 2-part problem. Part I, using partial fractions. So it's nice of them to tell us this, although you need to identify this on your own, even if they don't tell you. But using partial fractions, solve the differential equation, obtaining an expression for x in terms of t. Notice it's worth 9 points. So this is quite a lengthy process. And then followed up by state what happens to the value of x when t becomes large. We'll have to look at that later because it takes the entire board just to show this part. But notice a total of 10 points, 9 plus 1. So for 10 points at my 7-to-5 ratio, 7 minutes for every 5 points of question, that means you have 14 minutes to do this problem. So expect it to take some time. Don't feel like you're necessarily taking too much time. What's more important is your mental ability to follow through the process. So let's go back to the board. And let's get started here. So here is the equation that they gave us. 5 dx dt equals 20 minus x times 40 minus x. When x equals 10, t equals 0. So the first thing we want to do is separate. So to separate the variables, our dx is already on top. So both of these x terms need to divide to the bottom here. 5 over 20 minus x times 40 minus x. So now our x's are with the dx, and we're going to multiply the dt to the other side, and the dt is all by itself. That's okay, don't worry about it. There's no t variable in here right now. As far as the 5 goes, it's a constant. You can do with it pretty much whatever you want. You can leave it here or you can move it to the other side. You could make it 1/5 dt if you wanted to. However, I've chosen to leave it here simply because I didn't want that fraction of 1/5 on the other side. It doesn't really matter. At first, your numbers might be a little different, but eventually you'll come out to the same place later on. So I chose to leave the 5 there. Now, they told us or gave us a hint, very nice of them, to use partial fractions. Well, we're at the point where we're at this integrate now. And remember, before we integrate, we want to simplify. What do we have to do to prepare it to be integrated? So when we look at the right-hand side, there's no problem with integrating that. But when we look at the left-hand side, there's not a basic formula for this. The top is not the derivative of the bottom. This is not a substitution. There's no trigonometry for identities, and it's not a substitution type problem. It's not a integration by parts, although there is a quotient, but it's not a quotient of unlike terms. So it's not that. So the 5th one was partial fractions. So again, if you train your mental thinking, you can hone in on what it is you're supposed to do. They were nice enough to tell us at the very beginning to do partial fractions. So here's the partial fractions. This here on the left, the 5 over this, is going to become a over 20 minus x. If you look at these denominators, they're simple denominators. If you need help remembering, go back to the partial fractions videos in further algebra to review. But these are simple denominators, so a over 20 minus x plus b over 40 minus x. Remember, I do it kind of a mental way. So if we're solving for a, it means we need to get a by itself. So we're multiplying everything by 20 minus x. So if you multiply by 20 minus x, this cancels. A is by itself. Over here, you have a 20 minus x. And over here, this 20 minus x cancels, just leaving you with this part right here. So what you want to do is you want to choose the number that will make that become 0. Remember, this one is canceled out. It's right here. So, because we multiply by 20 minus x. So when you put 20 in there, it becomes 0, and it cancels out the entire b term. So this is canceled out. A is now all by itself. We already canceled out this 20 minus x. So we just have to put 20 here. 40 minus 20 is 20. So we're left with 5 over 20, which reduces to 1/4. So A is 1/4. Now we want to do the same thing with b, so we're going to multiply everything by 40 minus x. So when you multiply by 40 minus x, it cancels this out, leaving with b. Now we have a 40 minus x right here next to the a, and over here this 40 minus x cancels out, just leaving us with the 5 over 20 minus x. For this one, we're going to choose x to equal 40, and when we plug 40 in, remember this 40 minus x is right here. We get 0, cancels out the a term, so b equals 5 over 20 minus 40 is a negative 20, so b becomes a negative 1/4, so be careful with those signs. So a is a positive 1/4, b is a negative 1/4. So now we can rewrite this side. Don't worry about the 5, it's already incorporated in right there is where your 5 went. So we have 1 over 4 times 20 minus x because it was a 1/4. So here's our 1/4 with our simple denominator. Then minus, because this one is negative, a 1/4 with the 40 minus x. Dx equals dt, and this is now what we want to integrate. So all of this here was that simplify part of this integration. Simplify, integrate. Again, we don't have to evaluate because there's no bounds of integration, but we do need to do the plus c. So when we integrate this, this one becomes, starts off with a positive 1/4 ln of 20 minus x. So the 1/4 is the coefficient, ln of 20 minus x. But notice the argument has, when you take the derivative of the argument, it's a -1. So you need to divide by -1, which gives you a -1/4. So be very careful. Don't forget to check and go backwards. So the derivative of ln of 20 minus x is 1 over 20 minus x. The derivative of the inside is a negative, which cancels this and leaves you with the positive 1/4. So make sure you take the time. Remember, you got 14 minutes to do all of this. So make sure you double check to make sure that's correct. That little sign can throw you off. Then over here, we have the same thing. So we have 1/4 is the coefficient. It would start off minus 1/4 ln of 40 minus x, but again, because the argument has that negative on the x, the derivative of that's a -1. Divide by a negative changes this to positive. So again, it occurred on both of those. Then the derivative of a differential is the variable. Don't forget that one. This is kind of like a constant. When you derive a variable, it becomes a constant. When you integrate a constant, it goes back to the variable. You add 1 to the exponent. So right now, this is like a t to the 0. You add 1 makes it t to the 1. Okay, so this becomes t, gets rid of the differential, and now you have the plus c, which is our combined constant for this whole thing, plus c on the right. So now we move into our find c stage. So we plug in the 10 and the 0. When you plug in the 0, the t goes away. Plug in the 10, so we get a -1/4 ln of 10 plus 1/4 ln of 30. 40 minus 10 is 30. Now, at this point, I don't want to mess with combining these together yet. We've got fractions in here. I don't want to multiply everything through by 4 because I don't want to make my c more complicated. And I also don't want to raise them up as exponents. So for right now, instead of trying to figure it out here, let's put the whole equation together first and see what we have. So back here again, now I put the positive 1 first. So 1/4 ln of 40 minus x. Then the -1 next, minus 1/4 ln of 20 minus x equals the t, and our c is this right here. Again, I put the positive 1 first, minus the 1/4 ln 10. And if you notice, there's all these denominators of 4 except on the t. So since we've already gotten c, now I'll multiply everything by 4 to cancel out those fractions. And I actually do 2 steps here to save a little bit of board space. So I'll multiply everything by 4. All those 1/4 cancel out, and don't forget to put the 4 on the t. Then, because we're dealing with logarithms and a subtraction, it means the arguments can be divided. So we have logarithm of 40 minus x divided by 20 minus x, so that's 1 logarithm, equals 4t, so don't forget to put the 4 on the t, plus, and here's another subtraction, ln 30 divided by 10, so we have 30 over 10, which is going to reduce to just 3. Now we need to get rid of this logarithm, so we're going to exponentiate both sides. Why exponentiate both sides? Remember, we're trying to make x the subject. So since we're solving for x, we need to get rid of this transcendental function, so we do the opposite. Exponentiate both sides base e. On this side, again, we have a plus. Exponentials do not distribute to add and subtract. Now that we've exponentiated it, this is in the exponent position. So this is an exponent rule working backwards. When do you add exponents? It's when you multiply like bases. So it's e to the 4t times e to the 1, and 30 over 10 is 3. So when you multiply like bases, that's when you add exponents. You're using the rule backwards. The e and the 1 cancel, giving you a 3 as your coefficient. So again, I kind of added an extra step here. We're going to multiply the 20 minus x to the other side. So we have 40 minus x. We multiply the 20 minus x to the other side. And the other side is just now 3e to the 4t. So we need to distribute this through our parenthesis. So we're going to distribute. So that gives us 60 e to the 4t minus 3x e to the 4t. What our goal is here is we don't want an x in the numerator and denominator. We need to solidify and combine that x into one term. So first we have to multiply it to the other side, distribute it. Now that we have everything into separate terms, now we want all the x terms on one side and the non-x terms on the other. So we're going to add this 3x e to the 4t over here. We're going to keep the minus x. So on the non-x side, we're going to keep the 60 e to the 4t, and we're going to subtract this 40 from this side over to that side. So the x terms go together, the non-x terms go together. Then we can factor out the x. That leaves us with 3e to the 4t minus 1. And these are already okay, they're all non-x. And then we divide by that to get x by itself. So x equals 60 e to the 4t minus 40 divided by 3e to the 4t minus 1. And this is the answer to that first part of the question, that 9-point part of the question. This is the bulk of the work, but I also want to show you that last part of the question. It's only worth 1 point, but I still want to show you how to do it. So just give me a second. I need to free up some board space here. Okay, here we're back at where we left off. This was the answer that we ended up with. Now that second part of the question says, what happens to x when t becomes large? And really what it means is, as t approaches infinity, that's becoming large, just going on basically forever, what happens to x, the value of x? Well, this really has to do with what's called limits, and Cambridge does not include limits in its syllabus. I wish they had at least a basic introduction to limits before they entered the calculus units, but they don't. So that's why I'm going to take time to explain this. It doesn't take a lot of time, but if you were to plug infinity directly into this, you get infinity times 4, which is still infinity, and e to the infinity is still infinity times 60. You're basically going to end up with infinity over infinity, which is not something that we can work with. So what we want to do is we want to divide the top and bottom by our e to the 4t. So we're going to divide everything in the top and everything in the bottom by e to the 4t. And what that gives us is, when you divide by e to the 4t, this just becomes 60. This is 40 over e to the 4t over, this now just becomes 3 minus 1 over e to the 4t. Now you might look at that and say, how does that help? It doesn't really make it look any better. You know, what's the difference? Well, the difference is this. When we plugged in infinity into this form, we ended up with infinity over infinity. Not helpful. When we divide everything by e to the 4t and push that variable into the denominator, what happens now when we plug in infinity? 4 times infinity is still infinity, e to the infinity is still infinity, but now infinity is in the denominator of a fraction. And if your denominator is getting large, as in continuing on forever, it drives the value of that fraction to 0. So you can play with some numbers and you can see that, you know, 1 over 1, 1 over 10, 1 over 100, 1 over 1,000. The bigger that the denominator gets, the closer to 0 the fraction becomes. So as t approaches infinity, these fractions approach 0. So what you end up with then is just 60/3, and so our answer is 20. As t approaches infinity, our value of x approaches 20. And that is that 1 point value there at the end of the question. And every point is important on a Cambridge exam, especially if you're fighting for that extra grade boundary. So you don't want to lose any point. This is easy to do once you understand what it is that you're looking for. And I hope this helps. So there we are at the end of differentiation, or differential equations, actually, not differentiation, differential equations. And as always, thank you for joining me in the Zoom room, and hope to see you again next time.